Today we're going to be talking about how to find the distance from a point to a plane. And in this particular problem, we've been given the coordinate point 1, -2, 4, and we've been asked to find the distance between this coordinate point and the plane, which is defined by the equation 3x plus 2y plus 6z is equal to 5. Now we're going to be using a formula for distance, and you can generate this formula yourself. If you look at a picture of a plane and a coordinate point off of that plane, really the distance between them can just be described as the component of b along n, or the scalar projection of b along n, where n is the normal vector to the plane, the vector which is orthogonal or perpendicular to this plane, and we can really just describe that as the magnitude of the dot product of this normal vector n and the vector b. The vector b here in this case is the vector from a point on the plane, any point on the plane, to this coordinate point which is off the plane. So essentially the vector that connects those 2 points. And then we divide that by the magnitude of n, remembering again that n is the normal vector. So we can go about doing it this way, but we'd have to find the vector b and then plug all of those pieces into this formula. Really what this formula is going to break down to, if you did that, if you did find the vector v and the normal vector n and you plugged all those in here and you simplified, really you'd get to this formula here, which is easier to use if you can remember it. In this case, when we have a coordinate point, in our case 1, -2, 4, these values here you can just think of as x sub 1, y sub 1, and z sub 1. And we can plug those directly into our formula. We also need the values a, b, c, and d, and those come directly from the equation of the plane. So again, here we have a, b, c, and -d, I'll talk about that in a second, which come from the equation of the plane. These are just the coefficients on our x, y, and z terms, and then we have this constant here. So again, the coefficient on the x term here will be a, the coefficient on our y term will be b, and the coefficient on our z term will be c. And that should at least help us to start to see the relationship between these two formulas, because here in the denominator we have the magnitude of our normal vector. Well, remember how we find the magnitude is with the distance formula here, where we square each of the components in our normal vector. And if we remember, the normal vector we get just by taking the coefficients on x, y, and z. So looking at the equation of this plane, we know that the normal vector is the vector 3, 2, 6. If we want to take the magnitude of the normal vector, we just do 3 squared plus 2 squared plus 6 squared and take the square root of that sum. So in fact, the denominators of these two formulas match up exactly. This square root of a squared plus b squared plus c squared is the same as this magnitude of n, the normal vector. It's just really the numerator that we've significantly simplified here. So now to talk a minute about -d right here. In this formula where we have a times x sub 1 plus b times y sub 1, etc., we have this plus d value here. Well, we're taking these values, assuming that the equation of the plane is in a form such that all non-zero terms are on the left-hand side, and this equation is equal to 0 on the right-hand side. So it's essentially taking values from the equation. If on the left-hand side here we had -5, and the right-hand side was equal to 0. So if this were in the form 3x plus 2y plus 6z minus 5 is equal to 0, then we'd just be able to take this -5 and plug it straight in for d. But when the constant is over here on the right-hand side, we have this +5 over here, we have to treat it as -d. So in this case, when we plug in for d, we're going to plug in a -5. Because in order to get from -d to +d, we need to multiply this value by -1, and 5 becomes -5. So plugging in here for +d, we'll plug in -5. If the value over here on our right-hand side was a negative value, then we'd be plugging in a positive value here for d. So it's just really, if your constant is on the right-hand side, you're going to plug in that constant with the opposite sign. So since our constant is over on the right, instead of 5, we're plugging in -5. If your constant is over here on the left, you plug it in exactly as it is, including the sign in front of it. So if it were over here on the left, we just plug in -5 directly as it is. So those are the values you're going to pull out from the point and the equation of the plane. We're just going to start plugging them into our formula here. So our value of a comes directly from the equation of the plane. That's 3. So we have 3 times x sub 1, which we know to be 1 from our coordinate point. So 3 times 1, plus b here is 2, the coefficient on our y term in the equation of the plane, multiplied by the y value from our coordinate point, which is -2. Then here for c, we're going to get +6, which comes from the equation of the plane, so 6 times z sub 1, which comes from our coordinate point, that's 4. So we add all of those products together, and then here, remember, we have this plus d. We're going to be plugging in -5. So plugging in for positive d, we're just going to get -5 here. And then in our denominator, we have the square root of a squared. Well, 3 squared is 9, plus b squared, 2 squared is 4, plus c squared, 6 squared is 36, so we get 9 plus 4 plus 36 in the denominator. We want to take the square root of that sum, and when we simplify here, we have 3 times 1, which is 3, 2 times a -2 is a -4, 6 times 4 is 24, and then -5, and in our denominator, we'll get 9 plus 4 is 13 plus 36 is 49, so we get the square root of 49. Now if we continue to simplify here, remember we're finding d, which is the distance between the point and the plane. So d is going to be equal to 3 minus 4, which is a -1, plus 24 is a +23, minus 5 is a +18. These here are absolute value bars. So if you get a negative value, you want to just go ahead and make it a positive. In our case, we already had a +18. In our denominator, we have the square root of 49, which is going to be a positive or -7. But again, here we want to take the positive value, so we're going to get +7. That tells us that the distance between our coordinate point and this plane is 18/7. And that's all you need to do is pull out the values from the coordinate point and the values from the equation of the plane, plug them into this formula, and that'll give you the distance between the point and the plane.